Welcome to Zaption Tour 4.7 Arithmetic Sequences. There's 7 boxes. The essential understanding in this lesson is this, is that when you can identify a pattern in a sequence, you can use it to extend the sequence. So that's what we're going to be learning today. So let's talk about the first box here is going to be called extending sequences. So the first thing that we have to understand is that a sequence is nothing more than just an array of numbers. That's all it is. It's an array of numbers. So here's a sequence, for example, right? 5, 8, 11, and 14, and so on and so forth. So this right here is called the sequence itself, and each of these little pieces, each number in the sequence is called a term, okay? So the term and a term. And the way that we identify terms is with a subscript. So for example, this is the first term, so we call it a sub 1. That represents the first term. This is the second term, we call it a sub 2. This is the third term, we call it a sub 3. This is the fourth term, and we call it a sub 4. We do this so that we can identify terms in the sequence. So for example, I could tell you, all right, the second term of the sequence is a value of 8. The third term has a value of 11. The fourth term, so on and so forth. So as we extend this sequence here, okay, the general term we can represent as a sub n, just the general term in the sequence, a sub n, all right? Now, the next term after a sub n, this is the interesting part. Notice that these numbers are just going up by ones, right? Every single time. So starting with the first term, 1, 2, 3, 4. Well, if I'm talking about the general term here, then the very next term in the sequence has to be a sub n plus 1, whatever term I'm at. So that's very important to understand that the subscript a sub n plus 1 means the term after the term that you're currently on. So that means that the term before the term that you're currently on, this one over here, if this is a sub n and this is a sub n plus 1, then this term has to be a sub n minus 1. So it's very important that we understand these three little subscripts here. So a sub n is our general current term. A sub n plus 1 would be the term that's right after it, and a sub n minus 1 would be the term right before it, okay? So we're going to practice extending these sequences here, okay? So let's ask ourselves this. We have 5, 8, 11, and 14. So how do we get from here to here? How do we get from here to here? How do we get from here to here? So what do you think the next 3 terms would have to be in this particular sequence? Hopefully you see that we are adding 3 to each of the previous terms to get the next term. So the next term would have to be 14. If I added 3 to it, I would get 14, 15, 16. That would be 17. If I add another 3 to that, 17, 18, 19, 20. And if I add another 3 to that, I would get 23. Okay? Let's try part B right here. This represents a sub 1. This represents a sub 2. This is the third term. This is the fourth term. How would we describe this pattern? So how do we go from here to here? How do we go from here to here? How do we go from here to here? So what would be a sub 5? What would be a sub 6? And what would be a sub 7? Well, we are multiplying by 2 each time. We're multiplying by 2, multiplying by 2. So the next term in the sequence would have to be 40. Then we multiply by 2 and we get 80. Multiply by 2 and we get 160. Okay, box number 2 is you try. I want you to describe the pattern in each sequence. So how do we get from the first term to the second term to the third term? What's the pattern that you see? And then what are the next 2 terms? So this is going to be a sub 1. This is going to be a sub 2. This is going to be a sub 3. A sub 4. Dot, dot, dot means we continue on in that fashion. So what do you think a sub 5 is going to be? And what do you think a sub 6 is going to be? Hopefully you got the right answer. But here's the solution. When we say to describe the pattern, we are dividing the previous term by 2. So 40 or 400 divided by 2 is 200, divided by 2 is 100, divided by 2 is 50. So that means the fifth term would have to be 25, and then 25 over 2, or you could represent that as 25 over 2 as a decimal, which is 14.5. That'd be fine too. Box number 3 is the title of this section, and it's called Arithmetic Sequences. And an arithmetic sequence is just a very special type of a sequence. So what you have here, I have A, B, and C. I have 3 different sequences here. Each one of these sequences is arithmetic. I wonder if you see a pattern. For part A, how do we get from 3 to 8, from 8 to 13, from 13 to 18? And part B, a different arithmetic sequence. How do we go from 6 to 9? How do we go from 9 to 12, 12 to 15? And then part C, another arithmetic sequence. How do we go 10 to 4, 4 to -2, -2 to -8, and so on and so forth. So what do you see that's special about an arithmetic sequence? Hopefully you see it. If not, here it is. An arithmetic sequence, the definition for an arithmetic sequence is a sequence that has a common difference. So I'll write that down for you. It is a sequence with a common difference. So what do I mean by that? What I mean by that is this. If you take any term that you see in an arithmetic sequence and you subtract off the previous term, that term will always be constant, and we call that common difference D. We call it common difference D. So for example, in this particular case, right, the common difference would be 5, right? Each term is just the term before it plus 5. In part B, take any term that you want and subtract off the term before it. So 15 take away 12 is going to be 3. 12 take away 9 is going to be 3. 9 take away 6 is going to be 3. So the difference would be 3 in this case. So the D would be a value of 3. In this case, the common difference would be a value of 5. And in this case, the common difference would be, if I take any term, 4, and I subtract off 10, I would get -6. So a common difference is allowed to be negative. It's also allowed to be positive. So an arithmetic sequence is just a special type of a sequence in which that each term is separated by a common difference. Box number 4, I've given you A, B, C, D, E, and F. And the directions are this. It says only one of the following is an arithmetic sequence. Which one is it? And then what is the common difference? See if you can take a look at it and figure it out. Hopefully you see that the answer is D. This is the only one that has a common difference, and the difference happens to be 1. Every other sequence on the page, A through F, is not an arithmetic because the difference is not constant. D is the only one in which it is. In box 5, we learned that there are 2 different ways that we could write arithmetic sequences. We could write them using a recursive formula, or we could write them using an explicit formula. This is a very important box to understand. So the definition for a recursive formula is a function rule. So it's a function rule that relates each term of the sequence after the first ones to the one before it. Okay, so I'm going to talk more about that. An explicit formula is a function rule that relates each term of a sequence to the number term itself. And I'm going to show you exactly what we mean by each of these. So let's take, for example, this sequence here. Okay, it is 7, 11, 15, and 19. All right. So we note here that this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4. Okay. So a recursive formula would be this. We would define the very first term. We know that a sub 1 is equal to 7. That's what it says. And then we would say, okay, the next term in the sequence, so a sub n plus 1, the next term in the sequence, is nothing more than the term before it, which would be a sub n, plus the common difference d. So this is the way that we could represent a recursive formula for the function. So in this case, the specific one would be this. A sub n plus 1, so the next term in the sequence is just going to be the previous term, right? A sub n plus, and the common difference happens to be, in this case, if I take 7, and I have to add 4 to get to 11. So it would be a sub n plus 11. And you have to define your first term, because it says after the first one to the one before it. So we define the first term, and then we say the recursive formula would be this. Now, the explicit formula relates each term to this number in the term. So the explicit formula would be this, okay? A sub n is equal to the very first term, whatever it happens to be, a sub 1, plus n minus 1 times d. So this is a very, very, very important formula. Notice that it is taking this subscript n and making sure that it matches that number here. Okay? So let me give you an example for this one, all right? The general explicit formula would be a sub n is equal to the very first term, which happens to be 7, plus n minus 1 times the common difference, which happens to be a value of 4. So simplifying this, I would get 7 plus, this would distribute, 4n minus 4. And now I can clean up the 7 minus 4. 7 minus 4 is a value of 3. So I would get 4n minus 3. So the explicit formula would be 4n minus 3. So let me talk a little bit more about the explicit formula, okay? Here's what this says. We know, like for example, the fifth term in the sequence, the next term in the sequence would have to be 19 plus 4. That's what this thing tells me over here, the recursive formula. So 19 plus 4 is a value of 23. So now I know that the fifth term is a value of 23. Well, that's what this will tell me if I plug in at 5, a sub 5. It would have to be 4 times the value of 5, right? And then I would subtract off the 3. So that would give me 4 times 5 would give me 20 minus 3. Wait a minute. Oh, I see my mistake. 7 minus 4 is a positive 3. There we go. That was an easy one. So therefore, I would get 23. So notice that the explicit formula will tell me any term of the sequence that I want, because it is relating the term in the sequence to the number term itself. So let's do another one real quick just to make sure we have it. So a sub 6. So I want the value of a sub 6. Well, I know in this particular case that if I just add 4, I would get an answer of 4, 5, 27, right? That's pretty easy. But if I use the explicit formula over here, for example, if I plug in a sub 6, it would be the very first term, which is 7, plus the quantity of 6 minus 1, because remember that number matches for my n, times my common difference, which in this case is a value of 4. So this is going to give me 7 plus 6 minus 1 is a value of 5. And then I multiply that by 4. And there we see that we get 27, which is exactly what we would get here as we knew. Okay, box number 6, what we're going to do is we're going to write an explicit formula from a recursive formula. So they're giving us that the very first term is 19, and they're telling us that the next term in the sequence is equal to the term before it plus 12. So I'm going to go ahead and write out the first couple of terms, okay? A sub 1 is a value of 19, okay? And then it's telling us that the very next term in the sequence, that's what this part says, okay? The next term in the sequence is equal to the previous term plus 12. So to get a sub 2, I would take the previous term and then I would add 12 to this, okay? So if I add 12 to this, I get 9, 10, 11, I get 31, all right? If I go to my next one, the third one, again, I would take the previous term and I would add 12 to this. Well, that would give me 43, okay? And if the next term, I would add 4, or a sub 4, I would add 12 and I would get 55. And then so on down the line. So what we want to come up with is a sub n. What is the explicit formula? Well, we know this. We know that a sub n has to be equal to a sub 1 plus the quantity of n minus 1 times the common difference. So that means that we know the first value, it's worth 19, plus we have an n minus 1, and we know the common difference in this case happens to be 12. So all we have to do now is simplify. So we get 19 plus, this would be 12n minus 12, and this would give us 12n, and then 19 take away 12 is a positive 7. So 19, or 12n plus 7. So the explicit formula would be 12n plus 7. So you can check to see if this is right. That if we plug in, for example, a 3 for n, we should get a value of 43 out. So is it true? I can check. Is a sub 3? It would have to be 12 times the value of 3 and then plus 7. Well, there it is right there, right? That would give us 36, and then we would add 7, and that would give us a value that's equal to 43. So this must be the explicit formula. In box number 7, we're going to go the other route. It says write a recursive formula from an explicit formula. So they give us that a sub n is equal to 5n plus 2. So let's go ahead and write out the first couple of terms here, okay? What would a sub 1 be? Well, we would plug it in, right? This would be 5 times 1 and then plus 2. So this would give us a value of 7. So a sub 1 would be a value of 7. Okay, plug in a 2. I would get 5 times 2 plus 2. That would give me 10 plus 2. That would give me a value of 12. What would the third term be? Well, I would just plug in 5 times a 3 plus a 2. That would give me 15 plus a 2. That would give me 17. So now take a look at this sequence. Is it arithmetic? Well, yeah, because to get from 7 to 12, we'd be adding 5. To get from 12 to 17, we'd be adding 5. So it looks like to me that the common difference in this case is a value of 5, and it looks like the very first term is a value of 7. Well, if we have all that information, we could write the explicit formula. We know that a sub n is equal to a sub 1 plus the quantity write a recursive formula. Yeah, we already have the explicit one. Write the recursive formula. So the very first term is 7, and we would say that the very next term in the sequence, a sub n, is equal to the term before it, a sub n minus 1, and then we would add on that common difference. So a sub n minus 1, we just write as a sub n minus 1, and the common difference in this case is a value of 5. So the recursive formula would be a sub n is the previous term plus 5. And the explicit formula would be a sub n equals 5n plus 2. That was given to us.